I hope you've had a chance to view my previous videos on the periodic table and bonding. Before we can go on to discuss chemical reaction equations, we must define the term mole. Chemists use the word mole to describe a quantity of particles. A week of days is 7 days. A dozen of eggs is 12 eggs. A dozen corn cobs contains 12 corn cobs. A dozen of anything contains 12 of that thing. A mole is Avogadro's number of things. Avogadro's number is 6.022 times 10 to the 23rd power. Literally a 6 with 23 zeros behind it. So Avogadro's number of things is 6.022 times 10 to the 23rd things. A mole is 6.022 times 10 to the 23rd things. The atomic mass of a hydrogen atom is 1.008 AMU. AMU stands for atomic mass units. 1 mole of hydrogen atoms has a mass of 1.008 grams. A mole, Avogadro's number, and the AMU are based on the carbon-12 atom. The atomic mass of the carbon-12 atom is exactly 12 AMU. A mole of carbon-12 atoms has a mass of exactly 12 grams. By definition, 12 grams of carbon-12 atoms contains Avogadro's number of atoms. Avogadro's number has been determined from this definition to be 6.022 times 10 to the 23. 1 atmosphere of pressure is 760 millimeters of mercury, or 14.7 psi, or 101,325 pascals. 1 mole of any ideal gas fills a volume of 22.414 liters at 0 degrees Celsius and 1 atmosphere of pressure. 1 mole of any ideal gas fills a volume of 24.465 liters at 25 degrees Celsius and 1 atmosphere of pressure. The volume of a mole of ideal gas is useful for a wide range of applications where the conversion from volume flow to mass flow and back are required. The mole as a measure of number of things, particles, and atoms is useful in writing balanced chemical equations. In a chemical equation, the atoms or moles of atomic elements are conserved. Only the bonding partners are rearranged. The simplest chemical equation might be 2H forms H2. In words, 2 hydrogen atoms combine to form 1 molecule of hydrogen, H2. We might also use the mole concept to say that 2 moles of hydrogen atoms combine to form 1 mole of hydrogen gas, H2. In the chemical reaction, the H atoms on the left are the reactants, and the H2 molecules on the right are the products of the reaction. The arrow indicates the direction of the reaction, from reactants to products. A double-sided arrow is a more realistic indicator in a chemical equation because conditions such as temperature determine the direction of the reaction. I'm deliberately leaving energy or enthalpy out of the equations until we establish what a balanced equation is. When 2 moles of hydrogen gas react with 1 mole of molecular oxygen, the product is 2 moles of water. The balanced equation is 2H2 plus O2 forms 2H2O. This time, the double-sided arrow is used to indicate the reaction could go in either direction depending on the conditions. We could also divide the whole chemical equation by 2 and get the same balanced equation. There would be just half the mole count of each reactant and product. When 1 mole of hydrogen gas reacts with 1/2 mole of molecular oxygen, the product is 1 mole of water. The balanced equation is H2 plus 1/2 O2 forms H2O. The chemical equation is balanced because if we count up all the moles of H and O in the reactants, they exactly equal the number of moles of H and O in the products. 2 H's plus 1 O equals 2 H's plus 1 O. The moles of elements or atoms are conserved across the equation. In a previous video, I presented the chemical equation for the formation of ammonia, NH3, from the reaction of nitrogen gas, N2, with water, H2O. I repeat that equation on the slide. On the left side of the equation, we can count 4 moles of N atoms. 2N2 equals 4 moles of N atoms. The equation is balanced because if we look at the right-hand side of the equation, we can count 4 moles of N atoms that are now bonded to the hydrogen atoms to form the ammonia. Likewise for the hydrogen H atoms. On the left side of the equation, we can count 12 moles of H atoms. On the right side of the equation, we can count 12 moles of H atoms in the ammonia. 4 times 3 equals 12. So the equation is balanced with respect to H atoms. This leaves 6 moles of O atoms on the left-hand side, so I added 3 moles of O2 on the right side of the equation to balance the equation, because 3 times 2 equals 6. So the overall equation is balanced with the elements N, H, and O accounted for. The left side chemicals are called the reactants. The right side chemicals are called the product. If we were to calculate the combined masses of the reactants and the combined masses of the products, we would find the masses were the same. Masses conserved across chemical equations. Earlier in this discussion of chemistry, when I was talking about nitrogen-fixing bacteria, in the formation of ammonia equation we just covered, we see a balanced equation as well as a stoichiometric equation. All equations must be balanced or the conservation of mass and the conservation of elements is violated. Stoichiometric means all the reactants are used up to produce products with no reactants left over. In stoichiometric reactions, all the amounts of reactions are measured so that the amount of reactant A and the amount of reactant B are tuned to the exact amount to use up all the reactants. In real chemical reactions, the amounts of reactants used up depends on the temperature and the original mixtures of reactants. We can think of cases where there's too much of one reactant and not enough of a second reactant, and the result will be leftover reactant. For example, if we add too much water to the ammonia reaction, the result will be leftover water. 2N2s plus 12 H2Os becomes 4 NH3s plus 3 O2s plus 6 H2Os. The excess water never reacts and ends up on the product side. We can confirm the elements are conserved because the number of N's, H's, and O's on both sides are the same. In real equations, we could use the double-sided arrow to indicate the direction of the reaction could go both ways or be an incomplete reaction depending on the temperature. Consider the chemical reaction of ammonia with oxygen. Ammonia can be burned with liquid oxygen, LOX, as a propellant for rocket engines. The early tests of the X-15 rocket plane used ammonia and LOX as the propellant. These tests occurred before the development of RP1 kerosene as rocket propellant. The balanced equation is shown. Note the double arrow indicating the reaction could go either way. 4NH3 plus 3O2 results in 2N2 plus 6H2O. Again, the equation is balanced because we have conservation of moles of elements on both sides of the arrows. 4 N's, 12 H's, and 6 O's. We might also cut the total moles of reactants and products by dividing both sides by 4. NH3 plus 3/4 O2 reacts to form 1/2 N2 plus 3/2 H2O. A more realistic equation, we could leave the left side the same, but put X's in front of the products to indicate mole fractions of product. We cannot determine the mole fraction of product without information on the temperature and pressure at which the reaction occurred. NH3 plus 3/4 O2 reacts to form 1/2 N2 plus 3/2 H2O. Might be more realistically written, NH3 plus 3/4 O2 forms XNH3 plus XO2 plus XH2O plus XN2 plus XN plus XH2 plus XH plus XO plus XNO plus energy. In the product side of this equation, we also release or absorb energy. The energy comes from the breaking of old bonds and the formation of new bonds. This energy released or absorbed is also an unknown quantity until we determine the temperature and pressure at which the reaction occurs. Likewise, in the water formation reaction, we could also expand the right side of the equation to include likely product species with unknown x mole fractions plus energy. H2 plus 1/2 O2 reacts to form XH2O plus XH2 plus XH plus XO2 plus XO plus XOH plus energy. Again, we would need to know the temperature and pressure at which the reaction occurred to determine the x mole fraction of the products and the energy released. We can deal with the energy first and then go back to discuss the chemical reaction table information that we would need to get the x mole fraction of products from the reaction. In my next video, I will demonstrate how to get the energy if the temperature and pressure are known or assumed. Thank you for watching. If you enjoyed my video and would like to help me make similar content, please hit like and subscribe.